In the previous video, I showed how to reduce this eigenvalue eigenvector equation down to here. When you do this, you end up coming up with this special matrix, this one, where you have the numbers along the diagonal subtracting your eigenvalue. This is an important matrix that you use to solve for the eigenvalues. We're going to solve for the eigenvalues of this matrix, the one that we talked about in class. To solve for the eigenvalues, you want to take the determinant of the matrix that we started with. When you take the determinant of the matrix minus the eigenvalue times the identity matrix, you come up with this. Whenever you're doing this operation, you'll end up with subtracting the eigenvalues along the diagonal. Here, we want to take the determinant. So as we remember, to take a determinant of a 2 by 2 matrix, we need to multiply A11 by A22 across this diagonal and subtract A21 times A12 along that diagonal. For this matrix, what we end up getting is this: 6 minus lambda times 7 minus lambda minus 3 times 4. And we want to set that equal to 0 because we're looking for the solutions to the homogeneous set of equations as described in the previous video. When you're doing the matrix algebra for this, you need to make sure to include your variables in your determinant. When you expand this, you end up with a larger set of equations. What you get is 42 minus 7 lambda minus 6 lambda plus lambda squared minus 12. Now you can simplify this a bit more. I like to take the variable with the highest power and put it on the left-hand side. I'm going to do that here. Now, we gather the terms together, come up with this equation. Now we need to find the roots of this equation. To do this, you're going to perform the following operation, which you've done probably many times before, which is factoring out your equation. Because we have a positive here and a negative here, we know that this is going to be two negative signs here. In this case, we see that it's 3 and 10. This means that this equation is equal to 0 2 times. 1 at 3, positive 3, and 1 at 10. These are the eigenvalues of our problem. This is the characteristic polynomial. And we can use these eigenvalues to find the eigenvectors, and I'll show that in the next video.